we're going to get into a body-centered cubic structure. So we've just finished up simple cubic, so now let's look at a little bit more complicated structure. So let's go ahead and draw this out, and we'll take a peek on it on our kind of slides too. So very similar to simple cubic, where we're going to have kind of atoms at each corner, and then the kind of key distinction for body-centered cubic is we're going to have this atom right at the center, so inside of our cube right here. So that's it. So body-centered cubic is a very kind of popular structure. So lithium, iron, vanadium, molybdenum. So lots of alloys that you use for basically to alloy metals with. So we can just assign our basically our vectors here in a second, but it'd be useful to kind of look at kind of the structure of this material. Now, BCC is typically a more brittle type material or structure. Why is that? Well, we're going to kind of see that when we kind of talk and look at our atomic packing factor. So we talked about last time the atomic packing factor, when it's large, when we hit that magic number, that APF of about 0.74, we get to kind of, again, where dislocations can move more easily. So let's take a deeper look at the structure. So let's go to our lecture notes here, and let's go to the next slide. So this is body-centered cubic right here, BCC. So we can see kind of some of the basis vectors. We'll write this out in a second, but you can see the difference, right? So in simple cubic, you saw that these corner atoms, these were the ones that were touching. But look at body-centered cubic. Because we have that atom at the center here, there's some distance now. So the nearest neighbors are not here and here. The nearest neighbor distance is actually, as you can kind of see here, denoted by these vectors, here or here and here. So that is the kind of the key aspect here, is the big difference between these other values. So now this value here, this A, is not equal to 2R. And we're going to kind of figure out what that is. So let's go ahead and those notations, and let's go back to our notes, and let's flip our computer once again. So let's go ahead and figure out and define some of the kind of these lattice vectors, these values here. So my atomic packing factor, I could denote it as here, or my atomic packing factor, my primitive lattice vectors. So I can go here, here, and here. So again, this could be, A1, A2, A3. So those are kind of your vectors. Again, I should have used the hat notation, but you can kind of fix those on your own accord. And you can kind of see the magnitude is A over 2. We're going to see why that is in a second. But what is, or now actually, you can see these are the nearest neighbor distance. So I'll draw blue lines. So all these atoms here, this is my nearest neighbor distance here. So all between these. So I'm going to actually erase this for a second. And let's go ahead and describe the nearest neighbor distance. So draw one more time. Here, 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 here. Just drawing this BCC structure. So now the nearest neighbor distance across the cell is right here. So if I were to draw this director, or this direction here, let's go ahead and draw here. This direction would be the 111 direction. The magnitude of that 111 direction, that's going to be 4R. That diagonal is 4R. Why is it 4R? Well, because when we look at our BCC structure, and actually I'm going to draw one more time here. Let's erase here. Let's draw our BCC structure. One more time. BCC. Here, 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 here. If I'm looking at this atom, I'm going to draw my nearest neighbors in red. So each of these atoms in red, the corner atoms, are length 2R away from that center atom here. So this distance here is 2R. This distance here is 2R, etc., etc., etc. So what is my nearest neighbor distance? That never changes. It's always 2R. But again, look at those are the nearest neighbors now. Also, you can kind of look at what's my number of nearest neighbors. Well, my number of nearest neighbors, NNN, but my nearest neighbors or number of nearest neighbors, I'm going to count 1, 2, 3, 4, 5, 6, 7, and actually one more here that I forgot to kind of draw in. here, right here. I have 8 nearest neighbors as opposed to 6 for simple cubic. And finally, if I want, or not finally, but if I also want to count the number of atoms in my unit cell, I still have cubic symmetry. So each of these corner atoms are an 1/8, and there's 8 of them. But I also have 1 atom right at the center of my cube. So that's 1. So actually I have 2 atoms in my BCC structure. So another difference there. I can also calculate what is my next nearest neighbor distance, or what is this lattice parameter here for BCC. Actually, let's go ahead and calculate that one out right now. So what is this lattice parameter, this distance A, right here? A is not 2R or BCC. So I'm going to have to do some geometry to kind of figure this out. So I'm going to draw basically this kind of basically a 2D, a right, basically a right triangle. I'm going to go ahead and I'm going to draw from across that diagonal. So I know that this is A. I know that this distance here is black. So I'm going to draw a triangle like this. Here, here, and across here. So I know that this distance, that diagonal across my unit cell is 4R. I know that this distance is A. I also know that this is A as well. So I know from, again, that A squared plus A squared equals C squared. If this is C, this last kind of parameter here. Let's go ahead and solve that in Mathematica. Even though we know what it should be, let's just double check that it's root 2A. But again, you kind of double check that out and make sure that C is equal to root 2A. So hopefully people see this. So if I have a triangle, let's just draw that one more time. A, C squared, so I'm looking for C. I know that hypotenuse C squared equals 2A squared. So C equals root 2A. So I've got this, I want to write A in terms of R. So I want my hypotenuse, which is going to be 4 times R squared. Is that equal? I'm going to solve 4R squared equals A squared plus A squared plus square root of 2A squared. And let's solve for A in terms of R. So should keep it like that. So hopefully you can see, let's make sure that that's correct. So 4 square root of 2, yep. So our distance here, our A is 4R square root of 3. So we can kind of write that down right here. Actually, it's shown right here. So A is equal to 4R square root of 3. So we've got that. So we got our last parameter. We know the number of nearest neighbors is 8 for BCC. We know that the nearest neighbor distance is 2. We know the next nearest neighbor distance is 4R over A, which is 4R over square root of 3. So now we can go ahead and calculate what is the atomic packing factor of BCC. So let's go ahead and do that. So I'm going to go ahead and draw my structure one more time. Just drawing the structure here. Here we go. So how many atoms? So my APF, I need the number of atoms, which is going to be 2 times what's the volume of atoms? 4/3 pi r cubed divided by A cubed, where A is equal to 4R over square root of 3. So let's switch again to Mathematica just quickly. So let's do 2 times 4/3 times pi times r cubed divided by basically 4 times r divided by square root of 3 cubed. Let's put a parentheses around that just in case. And let's do this numerically, and we get 0.608. So again, is that 0.608 for 0.68 value? Let's go ahead here. Is this our magic number of 0.74? No, it's less than. So again, BCC is not close packed structure. So that's the key aspect there, not close packed structure. That's the key thing to remember. All right, so we've done SE, BCC, now let's do FCC. So I'll see you all in the next video. Thanks. All right, see you then. Thanks.